All right, welcome back. So let's start thinking about really simple population growth models, and then we'll get a little bit more complicated as we go on. So one of the important things to remember is the reason we're doing this is because population growth models are essentially the foundations of the species interaction models that we'll use later on in class. So when we think about competition, mutualism, predation, those are all based on multi-species population growth models. Now the most simple way we can think about that, a population growth, is by a population will grow by births and immigrants, and then it will, depending on the amount of immigration and number of deaths, that population, if might not grow at all, right? If births equals deaths and immigration equals emigration, then the population size would stay the same. But any one of these can change for any variety of reasons, making a change in the population size. Now, for the purposes of these models, we're going to make it a closed system where there's no immigration or emigration. Now, this isn't necessarily realistic, but it's what we're going to be doing on for this. So, population size is going to equal n, right? So this n number is that population size. So n sub t means the population at some time t plus the number of births minus the number of deaths equals that next time step. So let's say for white-tailed deer or something, we have a 1 year. We know that they always have babies every spring. So, in 2020 here, we have however many million deer in Wisconsin plus the number of births that we have, in that spring minus the deaths that we've had since the last time we counted them. That gets us our number here in the next time step. So that t plus 1, just remember, is that next time step. So what we're going to be doing is doing a little bit of algebra here, right? So we have our original population growth model here, but let's bring this over here with this, and we get n of t plus 1 minus n sub t equals births minus deaths. So this is essentially just going to be the change in the population size is due to births and deaths here. That's kind of all we're considering in this model. Now, this is calculus notation. Now, I know most of you probably haven't had calculus, and that's fine. We're not going to be doing calculus. We're going to just be using some of the notation because that's what all the textbooks use. That's what, really we should be doing this in, but we don't really need to use the calculus. Now, the total number of births in a population and the number of deaths really depend on the population size, right? So the bigger the population, the more births, the more deaths we'll have. So one way we can kind of equilibrate for this is by doing a per capita birth and death rate. And what this is looking at is basically what percentage of the population will be born or and will die each year. So what we get is this dn dt, the change in the number, is this now a small b, which is the per capita birth rate, and minus dn, which is the per capita, or the d is the per capita death rate, and then you multiply the numbers to get the total number of change in the population. So we do some further algebra, factor out this n, and we get this b minus d here put together. Now we do something, or what I should say is we've been talking about populations growing all the time. But, look at this here. It could be positive or negative, right? If births are bigger than deaths, then this will be positive. If deaths are bigger than births, then the change in number would be negative. And that just means, the population would get smaller, which happens all the time. All right, now we do something a little funny. we take this b minus d and replace it with r to get the equation. The change in number over time is r times n. Now, what is this r? The r is the per capita, the instantaneous growth rate, what it's called, I should say. And what this is meaning is basically how, a given population, we know how many babies on average the females can have, and we know, how they react to weather or something. So we can create this R based on if we know B and D. Like, what are the probability of each individual necessarily going to die, and how many individuals, offspring that individual would tend to produce. So what we see here is that we get this really simple equation that the change in number is this instantaneous growth rate times the number, the population size. Now the thing is that this change in population size varies with population size, right? The bigger this n is, the bigger this number will be, the bigger the change will be. Now when we take this equation right here, this is just the exponential growth equation. And what we see in this is this r essentially never changes, right? It's unaffected by population size, and we'll see why that's important in a minute. But what we get then is this exponential growth model where we have the n sub 0. This n sub 0 is just that starting population size. And then we take e, the base of the natural logarithm. That's just because we're doing some fancy algebra with logarithms. Don't worry about it. But what we get then is that this r and this r are the same deal. And then the t again is just time, right? So we can know at any time what the population is expected to be if we know three different things: the starting population size, the instantaneous growth rate, and the how many time steps have gone. Now, we know that then this exponential growth is, we can find it sometimes, but we know it's not realistic, right? So with invasive species, these Australian rabbits, rabbits were brought to Australia in 1859 from Europe. They brought 20 rabbits, and by 60 years later, there were millions of rabbits on the continent of Australia. Rabbit numbers would have eventually leveled off due to just certain number of space. They're not just going to have piles and piles of rabbits everywhere, right? There's only a certain amount of food on Australia or any given place, whether we're talking about laboratory organisms or real organisms in nature. The population cannot just increase forever. Eventually, we see a flattening out. Now, this flattening out thing is due to things like running out of space, running out of food, or organisms competing with each other. And what we see is populations level out at what's called a carrying capacity. And that's the stable maximum population size that a habitat can support. Now, this curve right here, what we're seeing is what's called logistic growth, okay? And the logistic growth curve is really looking at modeling growth of a population with a finite environment. Now, what does that mean? That might mean food, that might mean space, it can mean a variety of different things. Now, what this is essentially doing is modeling what's called density dependence, where the growth rate, this R essentially, changes based on density. The growth rate depends on the density. So let's think of a little example here where we have some sort of, let's say, a petri dish full of bacteria. Okay, at low population, basically each individual bacterium has a ton of food, so the probability that it's going to starve is low, but because it has so much food, it can produce a ton of babies. So birth rate's going to be really high. But as the population size then gets bigger, right, birth rate will start to decrease. Apparently I can't draw a straight line, but sorry, birth rate will decrease because individuals will run out of food, and they won't have as much energy to put into making babies. Death rate then increases, right? So the more starved these bacteria are, the more higher probability that each one's going to die. So death rate increases. So that's with just simple competition here, but we can think about this with predation or parasitism doesn't really matter. So what we would say here is the R, the births minus deaths, is really high here, but this R over here, deaths are really high. There's more deaths, so there would be a really low R here. So how do we simulate this? We want to simulate a changing of this R value with time. So what we do is we start off with that exponential growth equation, and we do something to it. We add this whole part there. And this is what's going to do, this is what we're going to use to factor in carrying capacity. So remember that K is the carrying capacity. This N is still just the population size. So let's spend some time thinking about what happens when the population is small, and what happens when the population starts to get bigger and gets up towards that carrying capacity. So let's do a little bit of algebra here. Based on our equation, what we've got is, R times 1. Let's say it's an asexually reproducing species. 5,000 minus 1 all over 5,000. Right? So what we get here is R times 49.99, right? All over 5,000. What that comes out to is R times 0.9998, which is essentially just R. Maybe I should have kept this population, this 1 in here. We can just put it right back in, right? So then the change in the population size, this dn over dt, is going to equal R times 1. Because just remember this 0.99999 is essentially just 1, right? So what's going to happen is, let's say up here R equals 0.1. What this is going to mean is then this population is going to grow by 10%. Now, okay, if we only have one individual that grows by 10%, that means this is going to equal 1.1, right? The population will get 10% bigger, so the next time step we're going to have 1.1 individuals. That doesn't really make sense here because with the numbers we're using, but that's okay. What this means is this R is unchanged, and it's going to be maximum, this 0.1, when you have a really low population. So let's do something different, right? Let's say n is 4,800. So r times 4,800 we have 5,000 minus 4,800 divided again by that 5,000. What we get is r times 4,800. And this essentially becomes, right, 200 over 5,000, 0.04. And then when you take 4,800 times 0.04, you get r times 192. Okay, so now let's put this r of 0.1 in, and then what you get is 19.2. So with a population of 4,800 individuals, you're only adding 19.2 individuals. That's really very, very small portion of the population is actually increasing, right? We should expect a whole lot more individuals, 480 individuals, if there was, no effect of this carrying capacity, of competition at this carrying capacity. But, what we're getting is a lot bigger number here. That change in population is going to be a lot bigger. A lot small, even though this 19.2 is bigger than this 1.1, proportionally, the population is getting much, much smaller, proportionally. Now, so what's happening? At basically, in the beginning, when population is really low, there's lots of resources for everything. There's not that much going on. There's not competition, right? Species or individuals aren't bumping into each other. There's lots of space, lots of food. But at high numbers, high population size, later on in time, there's a lot of competition. There's little space and little food. Okay? So what we're doing is we're trying to figure out a way to model this carrying capacity. And while this does a pretty good job of that, we know it's false, right? We know that this instantaneous growth rate is not linear with population size. Basically, these four things, I should say, are assumptions that this model makes. And we know that right away that r is not a linear function of population size. R cannot respond instantly, right? So this model kind of assumes that this is very smooth and happening continuously, but animals don't work that way. Organisms, shouldn't say animals, plants, fungus, bacteria, whatever, oftentimes are synchronous with seasons, and they may only reproduce once a year. This also has nothing to say about the environment. But we know weather exists, right? There's other things out in the environment, so predators, competitors, parasites. So R does actually change quite a bit. And then this assumes that all individuals are equal, right? And we just know that is not true, right? There are plenty of, if we think about just like an oak tree, think about how many acorns an oak tree can produce. Now, this model would just count an oak tree as one oak tree, but a small oak tree is really, not going to produce very many acorns, as opposed to a huge 200-year-old oak tree is going to produce way more acorns, right? Because it's older, bigger, has more biomass, has more leaves that can then convert sunlight into seeds, right? So we know that this model, there's limitations to this model. So you might ask, well, why are we studying this model, right? Again, this is that another starting point, right? We're getting a little bit more complicated. We're putting in things like carrying capacity. But the properties of this model, even though we know it's false, give us insight into what's happening in nature. And so the main takeaways from this idea, this model, is that population growth slows basically from right here through, as we get closer to the carrying capacity, the population growth slows. So we can think of population growth as the slope at any one spot. So here, it's a real steep slope. Here, not so much, and here the slope is essentially nothing, right? Now the key to this model here is that it's an equilibrium model, and we'll spend some time thinking about equilibrium versus non-equilibrium models in the next lecture. All right, thanks, and see you later.